Okay, for this lesson, there's not a whole lot new in terms of content, just reviewing and connecting together some concepts that were already addressed. So for the first problem today, it says, find the indicated nth partial sum of the arithmetic sequence. Okay, finding the nth partial sum means we want to add up the first n terms. So for this particular example, it means we want to sum up first 25 terms in this sequence. Now, it told us that it was arithmetic. We could confirm that by checking the first order differences. 11 to 19 is plus 8. 19 to 27 is plus 8. 27 to 35 is plus 8. So it has that constant d of 8. Okay, one of the formulas that we already learned in this chapter was that you could find the sum of a finite arithmetic sequence with n terms using this formula right here. So specific to this problem, it would be s sub 25 that we're looking for. That same subscript goes here, be 25 over 2. A sub 1 would be the first term in a sequence. A sub n would be the last term in a sequence, or in this case, the 25th term, whatever the last number is that we are trying to find. So let's go down to, where are we at? We'll do an intermediate step here. So we know we're looking for s of 25. That's 25 over 2. We know that the first term in a sequence is 11. So the missing piece of information that we need in order to get the sum of the first 25 terms is we need to know what the 25th term is. What's a sub 25? So another thing that we learned prior to this lesson is the fact of we have a very predictable rule to use to get a formula to define an arithmetic sequence. So I believe that's already on here. So we know that the term in front of the n is going to be 8 because that's our common difference. And we know this number would be, what if there was one more term in front? That would need to be a 3. Once we have this explicit formula, we can find any term of the sequence we want. We want the 25th term, so we plug in 25 for the 8. Order of operations gives us 203. That's the missing piece in order to use this formula. That can type in our calculator right in the home screen as is. So 25 divided by 2, then open parentheses, 11 plus 203, and we get the sum to be 2675. All right, so we don't really need any advanced technology. We could have done that using paper pencil arithmetic. There was nothing overly difficult about that. It was convenient to use technology, but we really didn't need it. Assuming advanced technology is allowed to answer a question like this, we also can take a different approach. One of the more recent things we just learned was how to do summation notation on our graphing calculator. So what we could do is take this formula that defines that sequence, plug it in here. Unless we're told otherwise, we're always assuming we're starting with 1. So 1 up to 25, summing the first 25 terms of that sequence, with 1 being the first number that gets plugged in. We can type that in our calculator and obtain the same 2675. So we're going to go to math. We are going to get that summation sigma function. Now, when we're writing them by hand like this, we avoid using x, y's, and z's for the counting variable or the index of summation for reasons we've already discussed. For our calculator, though, it's a lot more convenient to just use x. So, 1, and this is 25, and then 8x plus 3 equals, we get the same 2675. So at this stage of what we know and don't know in this chapter, in order to answer this question, we have two options. We could use this formula from earlier in the chapter, we could use the advanced features of our graphing calculator that we more recently learned. Depending on which you prefer and what technology is available while you're answering the question, obviously both produce the same answer. They both work. Excuse me. All right. Second example here. Instructions are to find the nth partial sum of the geometric sequence. So we got 100, 100, 50, 25, and we want the sum of the first 10 terms. All right, so one of the things we learned prior to today's lesson is to find the sum of a finite geometric sequence. We can use this formula right here. So the S sub n, same as what we just did above. So we want S of 10 specifically for this problem. A sub 1 is the first term in the sequence. R is our common ratio. So from 200 to 100 is times a half, 100 to 50 is times a half, 50 to 25 is times a half. More convenient to put that in as a decimal in terms of typing it in a calculator, and then that top R gets an exponent that matches that subscript. So we have 200. And then open parentheses, and we want the top of that fraction inside of parentheses. Top of that fraction also inside of parentheses. So 1 minus 0.5, raise that to the 10th power, get out of the exponent, close for the top, divided by, open for the bottom, 1 minus 0.5, close for the bottom, close for the whole fraction. And for these problems where you're asked to get a sum, unless you're specifically told otherwise, assume that they want an exact answer. So that may or may not be an exact decimal. I'm not really sure. The safe way to go is math frac, and that will give us the exact sum, and that matches what's on here. Okay, now similar to what we just did above, depending on what you have access to in terms of technology, if you have access to a graphing calculator or Desmos or something else that will calculate summation notation or sigma notation, we could take that approach instead. So one of the things that we learned prior to this lesson is that if we have a geometric sequence, we can write an explicit formula for it in this form right here. It's a sub 1, which is the first term. Common ratio, which we've already said is a half or 0.5. Exponent is always n minus 1. So we can sum this expression from 1 to 10. Excuse me again. So math, get the summation notation function. I'm going to use x for the purposes of typing it in the calculator. Again, when you're writing this by hand, you want to avoid x, y, and z. Going from 1 to 10, summing the expression 200, 0.5, times 0.5, raised to the 10 minus 1 power. Whoop, not 10, I'm sorry. X minus 1 power. Delete. Minus 1. And then frac that answer. And same result. All right, another idea that we discussed prior to this lesson is that under certain circumstances, you can sum an infinite series or sequence, depending on how the problem is presented. So one of those situations where you can get an infinite sum is if it's geometric and you know that the absolute value of your R is less than 1. So this sequence we just stressed above, we know it's geometric. They told us so, and we can test it ourselves. We know the R value is a half, which is less than 1, so we can get an infinite sum. The formula that we learned was this guy right here. The infinite sum is going to be the first term divided by 1 minus R. R is still the common ratio. So we know that the first term is 200. We know the common ratio is 0.5. So that's 200 divided by a half. 200 divided by a half is 400. All right, now as far as using technology for this, the TI-84 graphing calculators do not have infinity as an option. So we can certainly write this. We're going to sum that sequence from 1 to infinity, and the formula that defines that sequence we already addressed above. The trick is, if we want to use technology, what can we put there instead of infinity? So as we already discussed in a previous lesson, we want to pick a large enough number here where we can correctly identify what that number is supposed to be, but not too large as to create a memory overload. Now, depending on what this particular expression is, will depend on how big that has to be in order to make that happen. And that's very much just a guess and check. There are no rules or hidden math teacher secrets that I'm withholding from you. If you want to get an infinite sum for this type of sequence, it just becomes a guess and check procedure in terms of getting that big enough value to identify this number without giving it a memory overload or making it so large the calculator will take too long to figure it out. All right, so we clear that stuff out. Go to math. Get the summation back again. We're using x for calculator purposes. 200 times 0.5 raised to the x minus 1 power. And I'm just going to take a guess of what if we try 100. What will that give us? So the 100 actually gave us 400. So 100, not that big of a number. It's not like we had to put in 10,000. The calculator didn't take that long to spit it back. It was pretty quick about it. And it turns out that a number as low as 35 will actually round to 400. So this by no means is an exact science. You're not going to be guaranteed to be able to get that number that you're searching for, but it is possible in terms of like this particular example where it wasn't too difficult to get that 400 without actually putting in infinity, just a large enough number to accomplish what we want to accomplish. All right, last example for today. Find the indicated nth partial sum of the quadratic sequence. All right, well, let's first do a quick review of what makes a quadratic. I'll recopy it down here. If we check the first order differences, we get this right here. So 1 to 2 is plus 1, 2 to 4 is plus 2, 4 to 7 is plus 3, 7 to 11 is plus 4. So seeing that these first order differences are not constant, we know for sure that that's not an arithmetic or a linear sequence. Well, it's possible that if it's not one of those, it could be quadratic. And the way we can confirm that or test that is to find the second order differences. So we have a constant second order difference here. So we know for sure that this sequence is quadratic. Now, when we addressed quadratic sequences prior to this lesson, we didn't address the sum issue. It turns out that there's not a single formula. Typically, there's not going to be a single convenient formula that's going to give us the sum of the first n terms of a quadratic sequence. So it's not nice and clean like it was here or here. Formulas do exist. If you're interested in seeing what those formulas are and getting an idea of how you could work with those formulas to get this sum, our textbook does address it, but we're not going to be taking that approach. When it comes to summing up the terms of a quadratic sequence, we are just going to do a technology approach. So if we're going to use technology, we're going to need, first of all, an explicit equation for that series. sequence. So I'm going to go to Stat Edit, get rid of my old data. We have 1, 2, 3, 4, 5 terms. So in L1, I'm going to put the number of the term. L2 gets the term itself. Do a quick check to make sure I type that in correctly. 1, 2, 4, 7, 11. Looks good. 1 through 5 in L1. Quit out of the list. Stat calc. Quadratic reg. The data I just put in is an L1, L2. Frequency list, we always want left blank for these guys. Store the regression equation. If we're going to do something else with this, we can put it right into Y1 if we want to. We're not going to be doing anything else with it, so I'm just going to calculate. And that gives us the explicit formula for that sequence. So now third time, or actually fourth time, same set of steps. We want to sum that sequence going from 1 to 15, because we want the first 15 terms. So typing that in our calculator, math, get that summation function back again. X is going from 1 to 15. 0.5 x squared minus 0.5 x plus 1. Enter, and we get 575. So let's recap. In Chapter 4, there were 3 types of particular sequences that we concentrated on: arithmetic, geometric, and quadratic. Lots of other types of sequences exist that have specific rules in terms of formulas and definitions and stuff, but these are the 3 that we're specifically responsible for in this class. Within each type of sequence, one of the types of problems was summing up a certain number of terms. So for arithmetic, if it's finite, we can use this formula, or we can write a summation notation. If it's geometric and it's finite, we can use that formula or write a summation notation. If these conditions get met, we can sum an infinite using that. That's guaranteed to work. This may or may not work depending on that expression, how nasty it gets. Most of the time, you should be able to get that, but it wouldn't be guaranteed. All right, for quadratic, there's not one clean formula to get a sum. You have to use a combination of different formulas, typically. If you're interested in learning more about that, see page 677 in your textbook. Otherwise, as far as what you're responsible for on quizzes and tests in this class, when it comes to finding the sum of a quadratic sequence, you're going to get the explicit formula, write a summation notation, and then go from there. So that wraps up this part of Chapter 9. Video's done.